It says that you're live on YouTube, but I don't see something saying, hi, this is Devin, that
Yeah.
you're recording yet.
Uh, should I actually do the recording? Because I think if I do YouTube live, it will automatically save on the YouTube.
I would do both. I think Alex just does both as like
Okay,
it's like
I'll
a
record the.
fail safe, really.
Okay, sounds good. So it's 12:25. I think we can get started. Uh, okay, so I'm gonna share my screen. So Alex is out today, which means I will give this lecture. Can everyone see my Chrome okay and hear me okay?
Yep.
Yes.
Okay, so just before we get started, remember that homework 4 is due on Friday. And if you haven't started, I would advise you to start now as soon as possible, because this is a much bigger homework compared to your previous ones. So yeah, please start your homework. And we do have office hour tomorrow and Thursday and Friday, so you can get help on your homework. And we have a lab that I did yesterday, and the material is in the announcement channel, so you can see the code pen we used during the lab, and there are some points that you will probably be using to draw maps and the graphical in there. There will be examples that you can use. So today we'll be talking about layouts. So far we learned about D3 and how you can actually draw things on DOM. You basically bind the data and then you say what you're going to append. This is great, but sometimes we might want to do more complicated layouts. For example, if you have a network or you have a tree, it will be quite complicated for you to actually calculate all the locations of your nodes, or like how your tree is going to look like. So this is where layouts get really handy. It will automatically compute all these stuff for you. So we'll be looking at pie chart and some hierarchy layouts, and finally the network layouts. Even though we don't like pie charts in this class, we'll still be talking about them because we'll be using this information when we're going to talk about chord layouts later. So to do a pie chart layout, we are going to start with this simple line, like pi equals d3.pi. So d3.pi will basically calculate the pie chart layout for you, and then you input the data in there. But it only calculates the layout. So another function that is really handy is d3.arc. So .arc is a path generator, similarly to the path generator we use in the homework when we are doing geographical layout. So this is doing like arc layout, path generator.
And Haihan, one person posted in chat to zoom out the page. I assume they want the font larger.
Okay.
But correct me if that's incorrect.
Is this better, I guess?
Yeah, that looks better.
Sounds good. Okay, so yeah, we just talked about pi and arc. So these are all implementing D3 already. So we have an example here. It's pretty simple. We're gonna look at this. So first we define this data input. So we're doing the, so this is the mobile system information. So like if you're doing operating system Android, there's 82.8% share of the market, and etc. So we basically, this is pretty standard. You define a width, a height. Here we do a radius. We're gonna be using this later. So this is how you define your pie chart, like what is the radius of the pie. So we first have a SVG. Here we are saying this will be at the center of your canvas. We also have a color scale here. So D3.scale ordinal, this will basically say the first input will be matched to the first color. The second input will be matched to second color. Notice that we don't have a domain here. So scale ordinal will still work. If you don't input the domain, it will just automatically see if there is anything matched to the first one. If it doesn't, it match that input to the first one. And then etc. for the following input. So we're gonna first define pi equals to d3.pi. So this is just having a layout generator defined here. And now we say, what is the value to be calculated for this pie chart? Notice that d.share, this is corresponding to this value here. We're just saying you're gonna calculate this layout based on the value here. So if you have multiple values here, it's very important that you define what you're gonna be calculated based on, because this function doesn't know what you're gonna calculate based on. So this already have the layout, and then you can do a bunch of like customization thing. You can add padding. You can say like where it starts, and then we're gonna get the data out. So we're gonna input the data into the layout generator pi, and then we get the pi data out. So we can look at how this look like in here. Let me zoom in here so that it's okay. This is way too big. Okay, drag this. Okay. So here we have the calculated pi data. So for each one, it has a data. So which was the original data input for each share, for each like slice of the pie. And then it says where it starts, where it ends, what is the index, and then the value being calculated. So this is for each slice of the pie, it's calculated here. So we have that information here, but you can't really draw based on this, which means we need to have this d3.arc. So this will actually generate the path that we'll be drawing. So we're going to define this let arc equal to d3.arc. So we define a function like this. And then we're saying what is the outer radius and what is the inner radius. So the outer radius is what the radius of your pi will be like. So inner radius, we have 0 here. If we don't have a 0, it will give us like donut pi, donut chart. So if we define this to be, let's say 20, you have a hole in here. So this would be particularly useful when we're doing core layout in the following, but we're gonna have it 0 here because we want a pie chart. And then you can also do a bunch of padding setting with arc itself, but the Mike Bostock himself, who made D3, says it's better if you do the padding with pi instead of arc. But just you can do this as well. So we can look at what it looks like when it generates. So we input this pi data, the first value, first element of the array, which is this whole thing. We input in arc, and then this is what we got. So this is very similar to what you get from your homework when you're doing math. So it basically tells the path, which is the D input for your path element. So now we're actually going to do the drawing. So we have that groups, and then we select all the G elements, bind the data, and append G based on the data input. So notice that we actually select all G and bind the data to the G. And then when we append anything to the G, it actually will inherit the data input from the parent. So if you append anything in that G, this path will still get the data from its parents, which was the pi data. So we can actually do append path and then attributes D, arc. So we input the path generator in here, and the path generator is going to take in all the data from the pi input, the data here, and then get the D attributes that you want. And then we're gonna fill the pie based on the operating system. And then this color is a scale that we defined previously. And remember I said you don't have to have a domain. It will just say if something has been matched to range already. If it doesn't, it will just match to the next available range, input in the range. And then I'm gonna add some label. So if you look at the output here, we have the label right at the center for a slice. So to do this, for each G element we appended, we're gonna append a text element. For the text, we say what is the actual text you want, the content. So which is the d.data.os. So it's available in the data, and then .os, you retrieve this information here. And then you want to put it at the center, so we do a transform. The transform, we're going to translate, and then we can do an arc.centroid. So this will give you the center for that particular input. So this D is still the same data input from here. It will give you the translate information. And then we finally do something to make it right at the center. And then this is what we get. Any question about pie chart before we move on?
Hi, I had a question.
Yes.
Does the G stand for just one piece of the pie? Is that what the G represents?
Yes.
Okay.
So if you look at, so are you talking about this D or this attribute?
Oh no, the G. So like each G will represent one grouping of a pie. Is that kind of like the idea? And then the D.
So the idea is that you bind the data to the parent G here, right? So you have select. Let me select this so that we can actually look at this. So for each pie, we have a G layer here. And then for each G layer, we have a element of the array binding to it. So for example, this is our pie. This is hard to see now. So this is the data that we input, right? So the pie data here. We're gonna bind five elements that is in an array to each G. So each G already has its data, which is this whole thing. And then when we append anything inside this G, it will inherit whatever the parent already had, which was the data. And so this is why we have a D here. That was the similar to when we do like other D3 stuff, when we have like a D says what, like this is the data.
Okay.
Does that answer your question? So this is pretty similar to if you have something right after append G and then you just directly append anything here. But we're just making a groups of G's, and then for each one we're appending a path. And then the D is what this D is the required attribute for a path. Where do you go? So you see that path required to have a D input. So this is the D input that we put here. And then it will just get the data from here and input that into the arc function that we defined previously. And then that will give us the path D. And then this is just the anonymous function that we normally use for other D3 stuff as well.
That makes sense.
Yeah.
Thank you.
Okay. Any other questions about this? Okay. Then I'm gonna move on. So just notice that we have so the pi will calculate the end angle and the start angle. That's what you use to generate the arc. And then this is what the arc will generate. So that was the pie chart. And then we are going to talk about hierarchy layouts. So hierarchy layouts is something like a tree, or for example, the matrix here. I'm just gonna give you a preview of the like hierarchy stuff, like a tree. Like this will be like a hierarchy layout. We're gonna talk about how we actually do the tree layout later, but we're gonna come back to chord. So this thing accepts a matrix input. So how this works is, this is basically, we're saying there are 4 nodes. And then for each node, it will have a whole row in the matrix, which is, so this matrix is an array of array. So for each element in the outer layer of the array, it represents a node. And then for each node, it will say from 1 to 1. So from the node to the node itself, there are this value. And then this means from the first node to the second node, there is this much value going that way. And then etc. So this is saying from the first node to the third node, there is this much value. So diagonally, we're saying these are the values that goes within each node, and then the other ones are going outward. And then so it will always be an n by n matrix. So we represent matrix as array of array in code. And then to do this type of layout, we're going to use d3.chord. So this is pretty similar to d3.py. It will just return you a type of data that will be given to the path generator. And then we're going to also use .arc. We also talked about this previously. And then we're going to use another thing called d3.ribbon. So this will actually draw the give the path for the ribbon inside of the circle. And then, like I said, so because for each array, it's like one node to the other. So it has a source and the target. So this will, for the first one, it will be source to target node number 2. It has 5,871. So this is how you look at this. And then we're gonna talk about these while we're actually looking at the code. Okay, so moving on to the code. So this is just the input matrix we're gonna define here. This is like standard stuff for D3. We're gonna define an outer radius and the inner radius, because now we're doing a chord. It will be shaping like a donut instead of just a complete pie. And then we're going to define another color scale. This time we're going to define a domain, and then it has a range, are the color input. And then similar to we define pi equals d3.pi parentheses, we're going to define let chord equals to d3.chord. And then we add a padding angle here, which you can see that each one has this space, which is the padding angle that we defined. Okay, and then similarly, we're gonna have another function that's the path generator. We're gonna define d3.arc, and then we tell it what is the inner and the outer radius. So differently, we're gonna also define a ribbon. So this is the path generator that we're gonna use to draw these. So all of these are being generated by the ribbon generator. So the path, the arc generator generated this outer layer, and then within that, it's all generated by the ribbon function. So let's just see what chord matrix actually produce. So we can see it here, we input the data in there, which is the matrix that we defined previously, and then you can see that it generated these elements. So for each one, it has a source and a target. So for the first one, it says it goes from index 0 to index 0. So basically saying this value. And then it says it's 11975. So it matches. And then we're going to look at, like, let's see. So the second one, it says from 0 to 1. So which means it's this one. So from 0 to 1, it has this value input. Okay, and then you can notice that it still also has something called groups. So that's the last one, and that's an array. For this one, it basically says there are 4 nodes. So for each index is a node, which this stands for like this entire band that's like represented as this group. And then the previous ones are representing these like from this one to this one, from this one to this one. And then for each element in the groups, we can say that there's an index, and then what is the starting and the end angle, and what is the value. So it will be like adding everything up for this entire array, and that will give you this value. So that's like how much this will take. Okay, let's keep looking at the code. So now we have this input, and then we're gonna actually do the drawing stuff. So we're gonna append a G just like previously, and then so datum is basically saying you're binding a data array to a single element. So this doesn't do drawing or doesn't do enter, doesn't do exit, it just binds the data. So this is different from the previous one, and you can actually see that the entire thing. Where is it? Expect. So you can see that the entire chart is inside a single G element. That's what we appended here. And then for within that, we're gonna append a G based on the data that we have here. And then we're gonna give a class that's called groups. So you can see that we have a group here. And then we're gonna bind the data to each G here. So that's the what dot data. So datum will bind a data to a single element, and it doesn't do drawing, it doesn't do enter or anything. But data will bind an array of data to a group of elements, and they actually do enter and drawing or exit. So we're gonna select Alt G and bind the data. So this is different. We're gonna have 2 layers. So this is basically the outer layer of that cord, and then ribbon is the inner layer of the cord. So for the outer layer, remember I said the data generated here, there's one called groups. So we're gonna use chords groups. So we're gonna get that binded to this outer layer G, and then we're gonna append the G based on for each in that groups, which is 4. So we're gonna actually append 4G in the groups. And then within that, we're gonna append a path. So that's basically like for each one of these, we're gonna append a path. We append the path, and then we do fill, and then that's fill based on the index. So the index is already input here. We do the color, and then the stroke is the outer stroke. This is how we define. So you just do, where is it? Here. So you just do dot style stroke. You can also do attributes, I think. But you can do stroke or fill or anything, and then that's like, say it's darker than the original color. And then similarly, we're gonna have a D for the path. So that's always required when you're doing a path. It needs a D to actually draw it. We're inputting the path generator we defined previously. That's the arc, and then that will basically take all the data, which is this part, and calculate for each one what path will be. And then, so if we don't do ribbon, it will actually look like this. Okay. If we don't do, actually it's hard to, if we just, so we have the outer ring. So that's what the what we just did with the code here. We generated the outer ring, and then if we, so now we're gonna do the ribbons. So we're gonna append another G. So this G is defined when we appended the almost the outer layer, and then we're gonna append another G that's called ribbon, and then we're gonna have says its class ribbons. and then select all the paths in there, and then bind the data, and then append the data based on the append the path based on the data input. And then we're gonna input a different path generator. This time we are calling ribbon. Remember, the arc is the outer layer, and the ribbon is the one that generating the inner layer. So we're gonna use a different path generator here, ribbon. So ribbon will take in so all of these like source, source, target. It will generate a path based on this information. And then we're going to do fill similarly, and then stroke. And then, so this group ticks is what is drawing these ticks. It basically is using, let's see, we have a function here, and then it says like what is the starting and the ending angle, and then calculate that. Like it's just math stuff. And then we're gonna do d3.range. This will generate an array based on your input. It starts from 0, ended at this value, and then we're gonna have the step as the input, and then this will give you an array. So if it's 0, 10, 2, it will generate 0, 2, 4, 6, etc. So that's how you do the ticks. So we're gonna have select all group ticks, and then for each one, we're gonna say the data is calculated actually just from this one. So that's how we get the data. And then we're gonna do for each one, we're gonna append like a text here, and then that's being transformed so that it's actually rotating based on the input. Okay, any question about chord?
I just have a quick question. Do you have an example of like what kind of data you would use a visualization like this for?
I have it right here. Okay, so this is who is speaking in Lord of the Ring. So this is more complicated than what we did previously, but you can actually see like for Gandalf speaking where it happened, and then it will point to where it happened. So it basically gives you like a flow of where things go into the outer, into another set, or like in this case, from one variable to like we have different locations and where it is going. It's a way to represent like flow. We're actually gonna have another lecture just on like visualizing hierarchy and network, but we're basically focusing on how you actually write the code here. I hope that answered your question.
Yeah, thanks. Gives me a good idea. Thank you.
Yeah, so all of these, you might need to use them while you're doing your project later in the class. So this will be like, for this page, it will be really nice resource while you're thinking about your project. Any other questions before we move on?
Can you explain the data main data again?
So data will, so remember when we want to do enter and append, enter or exit, we want to do data because this is binding an array to a group of elements, and datum binds the data to a single element. It doesn't do enter or join. If you do like if you after this, if you do a join dot join, it won't do anything because that's what not datum do. You need to do data that will actually initialize the join or enter, etc. So this is like if you want to bind a long array to a single element and you want to do a bunch of stuff within that thing without like rebinding the data, but we are actually rebinding, but this is the data that we actually got from here, right? So we're retrieving that data and say this binds to the parent data and the dot groups, which is here.
Okay, thank you.
Okay, so that makes sense, right? I hope that I explained this a little bit clearly. Okay, let's. Any other questions for this part? Okay. So another way we have to visualize hierarchy data is tree. Tree is pretty common. Like if you have a family tree, you're gonna have like one ancestor and then their children and then their children. It's like a pretty obvious tree. And then we also dealt with tree in our homework 2, I believe. So we're gonna look at so it can have different data structure for trees. So this is pretty obvious that you have like a parent. So this is Eve, and then Eve has children, Cain, Seth, Abel, and then for like each one, they have their children name here. So this is very like direct way to show tree structure in the data, JSON data structure. So we can actually just call d3.hierarchy on the data like this. But when we're providing something like this, which I believe that's from your homework as well, and then how we deal with this type of input. So we're going to use stratify. D3.stratify will actually receive this type of data and then gives the same similar output to the D3.hierarchy, but they just expect different type of input. So the output will look like something like this. It will return a single node, and then for this node, it has an array of children. For each one, it will also be a node, and then if it has children, it will be also has an array and then says children, and then you can access that here. So it will always return a single root node, and then you get the tree structure from that. It also has like data, what is the name, if it doesn't have any parent, so it just parent is empty. And then you can also have two function like this, which is ancestor and descendant. You can get the ancestor node and the descendant node if you're calling on the node. Okay, we can look at the code we have here. So we're just like similarly, we're going to define this data. We're saying like the top level is just called top level, and then for the top level it has 2 children. The first one is called level 2A, the second one is called level 2B, and then level 2A has 2 children, son of A, daughter of A. So we're gonna try to get something else like this. So it has top level, and then we can actually collapse that, and then it has level 2A, level 2B, and then level 2A has 2 children, son of A, daughter of A. So because we have a nice input like this, so we're gonna just use the hierarchy, D3.hierarchy to get like to receive this data and make it something into like we're gonna use in the tree layout. So this is pretty standard setting up the SVG. I'm gonna define a D3.tree. So this is similar to the D3.py or D3.chord. It's a layout generator. So this will accept a data like this, and then it will give you like a layout tree map. We're gonna talk about these later, but let's look at the part that we actually draw. So like we're gonna tree map and input the root, which is the data that we got. Let me just make sure that we actually see the data, how it looks like. So this looks like something like this. So we have the children, so that's the top level. The data is called top level, and then it has children, which has 2 nodes. So for each one it has like the data, and then the first one, this doesn't have children. This doesn't have children. So we actually set the children to be null, but we'll talk about that later. So that's how we do collapse, is that we temporarily set the children to null and then have an alternative variable that will store the children, so underscore children. So this is storing its children, but because we collapse it, we don't want the tree map that we define to actually know that it has children. So it will not calculate the layout with the children input, but we store it somewhere so that we can still retrieve it later when we need it. So this is what this code is doing. And then so basically when we initialize this, it will collapse each children. So the third level will be collapsed. It will still show the first level and the second level. And then we're gonna collapse each children of the root. I hope that makes sense. It's a lot of words. And then we're gonna receive this layout calculated by tree map. So we can console log and see what tree data look like. So this is pretty similar to root that we got, but it has an X and Y value. So the X and Y value is what we're gonna use to assign the position. And then, so this is like just getting the descendants. So we're gonna there are two sections that are gonna tackle while we're doing a tree layout. We will have the nodes and you have the links. So we're gonna first do the nodes. We're gonna select all the nodes because we're also updating when we click. So we're gonna select all the nodes and then bind the data. After you bind the data, you say like, if you have any new nodes, you're gonna do node.enter and append another layer. And then this is how you do the animation, is that you first say it started from the old location. So it says it's starting from here. And then when you click, because it updates, so it needs to start somewhere. That's where we are pointing at somewhere. So where was I? So we're saying it's like it's starting from this y0 and x0. That's where you start. And then you're gonna do on click, and then we have a function that we defined click that's in the code below. We're gonna talk about it later. And then we're gonna append circle based on how many G that we appended. So this is node enter. For each one, we're gonna append the circle. And then we start the radius to be super tiny so that we can actually make the effect of making it like grow bigger. And then we're gonna also append the text for each node. So this is just doing the text, and then it says like where it starts, the location. And then we're gonna do update. So this is how you do the transition. So we're gonna first merge the nodes together. So that's basically merging the node enter and the original selection. So now we have all the nodes that's available on the canvas, and we're gonna do update to all of them. Then we're gonna say transition. So this is just saying we're gonna do animation here, and then duration is how long we're gonna do the animation for. And then we're gonna actually transition them to the proper location of the nodes. And for each node, we're also gonna transition them to the proper radius, which is 10. Remember, we defined the node to be super tiny, and so they actually have the grow effect. Just to see how it looks like. So you can see that it grows from there, and then it will also become tiny. Actually, it didn't grow. I thought it would grow. It must be something wrong. But we're gonna move on. Let's see where I was at. Okay, and then so this finished all the updates. It also has to remove any existing node if you're deleting something. So if we have this and we're gonna move to this, so this is what exit will work on. So here, not here. So node exit. So we're gonna have the exit selection part, and then we're gonna do a transition on those, and then we're gonna move them to their to the location that we're gonna move them towards, and then we're gonna remove them as well, and then also make them radius super tiny so that they have the effects of disappearing to the root node. And then we're also gonna make the text super tiny and then make them disappear. So that's what it's doing. So you grow this out, and then when you click it, it goes back, and then that's the exit doing the work. So that's the node section. We also have to update the links. So we're gonna select all the path that has the class link, and then bind the data. So the links, so we're gonna bind the data. This gonna bind for each one is the ID that we're gonna bind. So links is defined here. Where was I? Here. So similarly, we're gonna say like how many new paths we're gonna put in there, and then we're gonna enter. Why is this? It's insert into the G, I think. I have never used insert. Normally I just do append. Okay, and then dot attribute, and then we're gonna say it's the link class, so that we can actually select all these paths based on the class. And then we're gonna say it has a D, and then we actually calculate this how it looks like. So diagonal is a function that we defined below. So this is how you get a really curved path. So it has an input, and then this is how you generate the path. And then so that it looks like something like this. So we'll get the diagonal path back, and so here. So this is how you initiate, and then we update. So first we need to merge them together to do the update. So for update, we're also gonna do transition so that we have a nice animation going. So during the transition, we're just gonna make the D so that they actually look like something that we want them to look like. So this X0 was the previous one, the location, and then this is the final location that we want them to have. So that's how to make the animation for the link to grow. And then we're gonna also remove any link that we don't want anymore. So that's do the exit, and then you have a transition on that. And then you're gonna move them back to the place that you don't want. So like if you have this and then you want the link to go back, so you're gonna do that transition. Yes, and then you're gonna finally remove them. If you don't remove them, there will be many more links, and then it gets very lacking. It will lack a lot. Because you get so many elements on your screen. So if I remove this, fine. But so if you keep clicking, you can see like it's starting to lag because you get so many elements. If you don't remove them, it's just hiding in there. Okay. Any question about the tree? I know like I skipped a lot of the parts. I just want to like mostly talk about how you do the tree. You have like a circle and you have the path, and then you have to connect them. The animation part is less important compared to how you actually just do the layout. So homework for visualization, are you talking about the slider part lagging?
It's mostly drawing the map, I feel. I think it's a combination of everything that makes it lag a lot. So.
If it's the map shouldn't lag that much. I think you might want to check you're not just appending multiple layers.
Oh, I did check that. I think it's just my computer's too slow. So.
Oh, okay. Yeah. The scatterplot can lag a little bit. It lags on my computer as well. So it just might be something that if you're updating really fast, and it's a lot of points, and it can be slow. But if you just need to check that you're not just appending multiple layers, that's mostly the important thing. Okay. we're good on time. Okay, I'm gonna move on to another layout. So tree map. Tree map is another way to do hierarchy layout. It looks something like this. Oh, I don't want to do this. Well, it's not loading. Okay, great. But we'll have something like this. So for tree map, the way that you read this is within each color, it's divided into blocks. So that's like the children. And then we actually don't show the parent for these children. So all of these elements, they have the same parent, but they're just like dividing. And then for each one has a value. So we're gonna like see we can actually know like how much this take up. So the circle has a big one, like this has a pretty small one. So this shows like how much each child takes up, like how big the value is. So we're gonna look at tree map. So tree map has like, this will calculate your node x0, which is the left edge, and the top edge, like where it starts, and then x1, y1, which is the bottom edge. So that's like the standard stuff for your rectangle. You can calculate the width and height based on this information. So here we said you probably want to call root sort before you actually calculate hierarchy, because you probably want to put all your bigger children at the start, and then it's easier to calculate and easier to look like. So you see like we have all the bigger children, and then it divides into smaller ones. So we're gonna do similar stuff here, like initialize the SVG, etc. Different things, we're gonna do a d3.tree map. So this is what doing the layout for tree map. We're gonna have how big the canvas is, because it needs to know where to actually put stuff, and how to divide the rectangles. And then like we can add padding and round. I actually don't know what round do. So we can probably delete this and see what it looks like. It doesn't look different. Does it look different? Interesting. I actually don't know what round do. We probably, like, if you're interested, you probably can interested in this, you can probably look up the tree map implementation on GitHub. So this is basically a tree map of how different components of D3 within like each tiny, it's like a hierarchy. So within this is all in the D3-geo, and then all of these are in there. So this is like a hierarchy layout. All of these are inside the D3-geo. So like you can actually look at the link below, it says D3-geo, and then this is also in D3-geo, etc. Okay, so we're gonna talk about these later actually. So similarly, we're gonna do the data cleaning, or you can call it manipulation, I guess, because it's like input the data into the D3.stratify. And then we sort this, and then we also sum so that we know like the size. And then we put this inside the tree map. So this will give us the layout. And then for each cell, it says like you select A. So the reason that we use A here is that you notice this is like a link that you can actually open. And then you can actually see like this is where it pointed to. So A is how you do a link. So we have select all link and then bind the data. We want to get all the leaves to be the actual cells. We actually don't visualize the root. So that's why we bind the data, bind the leaves to the data. And then we enter a pen. So this is pretty pretty regular stuff. And then for A, we have to give it a target and then give it where it's linking to. So this is just basically telling it where it's gonna be linked to. And then we're gonna move it to so that it actually is where it's set, like it's supposed to be. So the x0 and y0, that's from the tree map calculation. And then for each cell, we're gonna append a rectangle. So that's just how we're gonna fill it up with rectangles. And then we're gonna do like attributes. It has an ID. The width, you calculate that based on the x1 minus x0. So that's the right side, the right lower side, and then x0 is the left side. So you do a minus. Similar with the height. And then when we do the fill, we want to get the ancestor color so that all of these, they share the same ancestor. So we have the same color for them. So that's why we have the fill. And then we're going to also do a click path. I think that makes everything inside clickable so that it's not just this little part is a link. You click anywhere in here, you can actually click it. And then we're gonna also do, this is like all the text stuff that we do for this. But the most important thing is that you can do tree map layout and then append like rectangles based on the layout. But this is a little bit hard to read in my opinion for a hierarchy layout. But it's a way to visualize things. And normally you would want to have interactions when you do this so that you can actually start with the outer ancestor and then you click it and then you can actually see what's inside. So that way you can actually still know what is the ancestor and what is inside. This doesn't tell you what the ancestor. Any question about hierarchy layout? We're gonna move on to network next.
Sorry, how do we know what's the parent of a node here?
I'm sorry?
How do we know what's the parent of a node?
A pattern of the node.
A parent.
Do you mean like
parent?
The parent?
Yes.
So like when you do this is a node, right? And then you get the ancestor. So for each node, it has a function like you can do descendant or ancestor. That will give you like what is the parent or the ancestor.
I mean
so
from
like,
the tree map. I mean from the picture.
Yeah, so you can't tell. That's why I'm saying this is not an interactive one, which is why I don't like when you do tree map, you don't do interaction. Because if you have an interaction, you can imagine that everything within this will collapse and will tell you what is the parent here. And then when you click on it, it will expand and tell you what is the component in here.
Okay, thanks.
There will not be a group activity today. We normally have those when we have theory classes. For coding classes, we don't really have group activities. Okay, I'm gonna move on to network. So networks, we have hierarchy layout. A tree is actually just a type of network, right? But we have like generate network. It's like a node to node, a node link diagram. So that's a way to actually render a network. So for example, this is a network, right? It's a node link diagram. And then D3 has like pretty comprehensive stuff while we want to like about rendering networks. And then this might be very helpful when you want to do your final project with networks. This like the stuff that you want to use. So for a network, normally like your JSON file will be like, it has a node. And then for each node, it will say like, what is the name? And then it has like maybe a group number. And then for each links, it has where it starts, where it goes. And then your link might be weighted, so it might have a value on there. And you can actually visualize this like if you can use the link stroke width to visualize how like the value of the links. So we are first we're gonna use the fetch module. So that's gonna load the data asynchronously. So we're gonna just take a quick look at that. I'm gonna scroll really down. Okay. Okay. So here is how you load. Why you want to load a whole file? You definitely want to use either this or await. We're gonna have another lecture on like this type of JavaScript. It basically, because this might take a while. So the way that JavaScript do is that it's gonna say, oh, it's gonna take a while, so I'm not gonna finish this right now. But this can be a problem because all of your later code is depending on loading this file. So this is why we do, first you wanna finish this, and then we're gonna do all of these. So this is telling JavaScript saying, you need to finish this first before we're gonna do anything below. So if you don't do this, and then you directly just, if you assign something to this, and then you're gonna directly use that below, it's gonna say like it's undefined or something. This returns a promise, and then tells it's wait this promise to finish, and then we're gonna use the output we get from that promise, and then do something about that output. So this is how we're gonna do asynchronous call. Like I said, we're gonna have another lecture on this. I'm gonna keep going. So a very important thing you wanna know when we do network is forces. So forces is how you modify the node's position and velocities. So if you can initialize all of your nodes like that before, so like this, and then force is how to simulate and then say where each node is gonna be. And then in this example, we actually used link force, charge, and center. We're gonna look at each differently. Like each thing do different stuff with the node. And then the way that we do this is, this should be a let instead of var. We let the simulation equals to d3.force simulation. This initialize, we're gonna do a simulation here, and then we're gonna say, oh, which force is it gonna use? So we're gonna first look at force link. So if we remove the force link, it's gonna just expand like this. They are all just nodes. So the link is this force. It's like a spring. It pulls two things together. It's not a spring. Spring still repel things apart. But this is what basically pulls the nodes that are linked together. So you can see that this is not moving like far away from the screen. So that's what the force link. So like when you do force link, you want to say like .id. So it says like when ID is specified, sets the node ID and accessor to the specified function and return this force. But you can actually just directly ignore this, and if you do a link and tell it what the links are, it will do it also. And then force many-body, this is a force that applied to each of the nodes. They are the same force that basically either pull the nodes together or pull them apart. So you can see that if we don't have a force many-body here, they're just gonna stand there. They don't move around because you don't really have anything to either pull them apart or, they're just there. Another thing, force center, this is a central force that gonna pull your nodes to the center so that they don't just randomly wander on your canvas. So if we don't have that, you can see that they're just like at some random location. They're not being pulled to the center of the canvas. So that's why we have center force. And then another thing is if we can have collide force. So for a collide force is saying for each node, it has a circle around it and saying other within this circle, there should be no other nodes. So it's basically avoid any collision for the node. And then the other type of force, we can have force X and force Y. So force X is having a force along the X-axis, and then force Y is along the Y-axis. So we actually have an example that I have here. So you can actually play around how each force look like. So you can say we want to move around. So this is the center force. So that's pulling everything to the center. And then, so charges, this is like how much each node repel each other. So you can see like if I make it really big, this is just gonna pull everything together because they attract to each other. This repels so that everything repels to each other. And then you can also set like a bunch of different things. So collision, it's not gonna be very obvious, but because other forces in charge here. But if you, this is ridiculous. Okay, this is less important, I think. But force X and force Y, so you can see that if you have a force that pulls other points towards a X location, so you can see that it's pulling towards this X location. So it's all this X. We can disable that. I can see force Y. So it's along the Y-axis, we have them pulling towards at a single Y location. Because we still have other force being selected here, so they're also going to have effect. So one of the another important thing is the link. That so that's the force for each the link here. So if you don't have that, you can just see like each node is just gonna be by itself. The link is what makes the, like you can actually see the network structure. So like for the force, like if you pull them apart, the force will adjust. So we can actually implement this in D3. So similarly, we have like D3 stuff. The link to, do you mean the link to this example, the D3 force testing ground?
Yes, please.
Yes.
You can just, I think you just Google D3 test ground and then it will pop up if it's not on this already. It's like, yeah. So we like initialize the SVG, and then we like, this is pretty standard stuff. Yeah. Thanks, Evan, for posting the link. So we initialize the simulation, says like we have the D3.simulation. So this is, we initialize the simulation function, and then we're gonna input each one. So we're gonna have the link, and then we're gonna say what is the force, and then we're gonna have a charge, and then what is the charge force, and then the center force, and then we define the center force here. So this is where you initialize the simulation, and then like I said previously, so this is loading the data asynchronously, so you must have a then, so says you first finish this loading, and then we'll do the following stuff, because it's all depending on this input. So that's the data that you got from this D3.json. So we're gonna just append like a layer of G, so that's pretty standard stuff. Let's get to the, we're gonna have a link layer. So link layer was the appended here. So we're gonna select all the lines. That's what draws the link between each node. So we're gonna select all the lines and then bind the data of the links. So remember that the network data has like a node and the links. So we're gonna wanna bind the link data to the data to the links, so that this is what actually will be the link information. And then we enter append lines, and then we like set the stroke width. And then we create another layer that will be the node layer. So we have one layer for links, one layer for nodes. So for the node layer, we're gonna bind data with all nodes so that there are different data actually. So we enter a pen circle. So for each circle, there will be a radius that is just standard radius for all the same. You can actually adjust this radius based on the value. So if your nodes have different weight, you can actually just say this is different. So like you can do the arrow something something here that you will give you different sides of the circle. And then we fill them with different colors. So here is we add another event listener. We'll see that later, but so this is just appending a title so that we actually know what. It actually doesn't show the title, I think. So if you hover, if you wait, like you can see that it has a little tooltip there. So that's binding, that's appending the title. So this is what the simulation get interesting. So we say, remember we already predefined the simulation function. That's the d3.force simulation that we defined here. So we're gonna use that simulation that we defined. So we're gonna say, what are the nodes? It's the graph.nodes. And what are the links? So the first link will use this link. So we're gonna input the data here. So simulation.on, this says for each iteration. So simulation is basically doing a lot of iteration of calculation of the nodes position so that they are at optimal position. They're saying for each tick, so that means like for each iteration, where are you gonna put your links and nodes? So the links and nodes are the groups of the links that we already appended and the nodes we already appended, but we haven't set their attributes yet because that's gonna be from the simulation. That's what's gonna calculate the location of the nodes and the links. So we're gonna use that information to assign the position of the links and the position of the nodes. So that's what it's very important to know is that when you do network and you want to use simulation, you don't want to assign their position outside the simulation because they are dependent on the simulation. And we also have that event listener we implemented previously. So remember that we have a call d3.drag and then on start drag end. So that is defined here. So when we do a drag, it will reset the simulation. So we have this network here, and you can notice that when I drag something, it actually based on the dragging, it will adjust this, and then when I release it, it will go back. So that's what the dragging will do. It says like when you start the dragging, it will just like restart the simulation, and then while it's dragged, you're gonna just move along with the mouse with this nodes. So this node will not listen to the simulation, kind of. It just basically where your mouse is gonna move. But other nodes are still inside the simulation. And then when the drag ends, it's gonna recalculate the entire simulation, and then it will be wherever you like the new simulation calculated will be. So this is network. Any question about network or forces?
We have one question in the chat asking if we can use this to simulate graph algorithms.
What type of graph algorithms are you talking about? Like, are you thinking about? Okay. Yeah, but like you can basically customize a lot of stuff with the simulation, and just remember that links. So the data is actually being updated, so you can actually directly just say the data and then get the source X and source Y. So the data is being updated when we input the data into the simulation. And then, so finally, this is not D3, but Cytoscape is another open source graph theory library written in JS. So Cytoscape, like you can use this as well, but we are not gonna really talk about this for this class because we're mostly focusing on D3. But this is another way to do this. Like you can use other stuff as well. I have used Gephi for network. Like Gephi is great if you want to calculate a bunch of network properties. So D3 doesn't really calculate the network properties for you, like the centrality or if like those kind of stuff. So those you need to either have another library. I don't think D3 will calculate for you based on what I know. So you probably need to have another library or use another, just use another completely new software. So D3 is mostly just like if you want to render something. Okay, I think that's basically what we have for today's lecture. How many are we? I think I'm doing pretty good on time. I can stick around and answer questions if you have any. But yeah, that's all the stuff I have today.